Fine. Now with this background, let us understand how this SN1 reaction takes place. In short, if I want to describe, SN1 is a two-step reaction. What are the two steps involved? Step 1 is formation of carbocation, and step 2, after formation of carbocation, the nucleophile attacks this carbocation to give the product. So let us take a very famous example of SN1 reaction, that is tertiary butyl bromide. When reacts with the undergoes SN1 reaction, or we'll call it as alkaline hydrolysis, you get this as a product, that is tertiary butyl alcohol. Just now we spoke that these all are CC bonds, they are non-polar covalent bond, but CBr is a polar covalent bond. This carbon carries partial positive charge. First, since it is a two-step reaction, step 1 is formation of carbocation, where first the leaving group departs from the substrate. This particular reactant is called as a substrate. So the loss of halide takes place. Over here, halide is bromide. After leaving bromide, what you get? sp3 carbon becomes sp2 carbon. It is a planar. The angle is 120. Once this carbocation is formed, it is electron deficient. So your nucleophile easily gets attracted to this carbon, and you get a product in the first step, that is step 2, to give you the alcohol, tertiary butyl alcohol, as a substitution product. So this is how in general we write down this reaction of SN1, or we represent the mechanism. So if it is a sp3 hybridized carbon, you have a leaving group. First leaving group will depart. You get a trigonal planar sp2 hybridized carbocation intermediate, and now nucleophile will come, attack this carbon and form the product. Now leaving group is replaced by the nucleophile. So let us see this video and understand SN1 reaction. So this is your substrate. This is a tertiary butyl, let's say tertiary butyl bromide, just now what we have seen. This yellow is your bromide, which will be a leaving group, and all other these are the CH3 groups. First CH3, second CH3, and third CH3. Now what is your it is a two-step reaction. So tertiary butyl bromide, the IUPAC name is 2-methyl-2-bromopropane. So you can give IUPAC name or a common name. Now first thing what is going to happen, that the bond between carbon and the leaving group is going to break. The leaving group departs from the substrate. The sp3 hybridized now has become sp2 hybridized. Now all are in same plane. So it is a trigonal planar geometry of the carbocation. Now what will happen? This carbocation, once it is formed, the nucleophile approaches this carbon, which is central carbon, positively charged carbocation, and forms the product, that is 2-methyl-2-propanol, and now you get a product which is highly stable. So if I see the energy profile diagram, as we go, the energy of activation goes on increasing, then the transition state is converted into intermediate carbocation, and then the nucleophile starts approaching to this carbocation. Again energy increases, second activation energy, and finally you get the stable product. The energy of product will be always less as compared to energy of reactant. Fine. So let us go ahead. So just now we have seen, this is so this is your reaction just now, what you have seen. This is your sp2 carbocation. Nucleophile is approaching it, and you get the product. And just now we have seen this animation where we had seen that there are two maxima. One, first transition state, where bond between the carbon and the leaving group partially broken. We have seen two transition states. Second transition state is the partial bond formation of nucleophile with the carbocation. In between those two transition states, we have an intermediate, that is carbocation intermediate, that is R plus. We have represented it with R plus. These are your reactants, these are your products. You can see the energy of reactants is greater as compared to energy of product. So let's understand again now the stereochemistry of this particular reaction with this mechanism. So this is your substrate. The substrate has this leaving group, and this is your electrophilic center, and this is your nucleophile. Okay, nucleophile is electron rich, and it is going to come to your carbocation or electrophile. Electrophile means something which will love electrons, and nucleophile is electron rich, right? So what happens over here? The energy goes on increasing, the first transition state, and then now here you can see the intermediate is formed. Now this is your nucleophile, this is your leaving group. No one is bonded to this carbon. The carbon is trivalent and therefore it is planar. Now your nucleophile has come and formed bond from the opposite side of the leaving group. But there are two possibilities. Either it comes from opposite side of leaving group, or it can come from the same side of leaving group. Because after formation of planar carbocation, it is possible that it can come from the same side of the leaving group. So you get a product where you will have nucleophile coming from the same side of the leaving group, or nucleophile coming from the opposite side of the leaving group. So here we have seen that it comes from opposite side in the first one. Now just now we have seen that it can come from the same side of the leaving group. So this is how stereochemically these two products are formed, which will be related to each other as non-superimposable mirror images if you have a chiral carbon, or they are the enantiomeric with respect to each other. So this is how we can explain the stereochemistry of SN1 mechanism, where you'll find that you get product where one product has orientation same as that of your reactant, and the other one has exactly opposite orientation if I compare with the reactant. So stereochemically you get these two molecules, but chemically they are one and the same. We cannot distinguish between enantiomers when we talk about chemical reactions. So what are the factors which will affect the SN1 reaction? Nature of nucleophile or nature of substrate, what kind of leaving group is there, and what type of solvent is used. These are the four factors which will decide the rate of SN1 type of reaction. So what are the factors which will affect the rate of reaction? Just now we have seen that when we write the mechanism for SN1, the first step what is called as a rate determining step, and it involves only substrate, not the nucleophile. Therefore rate mostly depends upon the type of substrate, concentration of substrate, and generally it is independent of the nature of nucleophile. So SN1 reactions are also called as solvolysis because many times your solvent acts as a nucleophile. The tertiary alkyl halides will be more reactive than secondary and primary. Why? Because tertiary alkyl halides are going to generate more stable carbocation if I compare with secondary or primary alkyl halides or uh, alkyl halides. The positively charged carbon atom of a carbocation has a trigonal planar geometry. Just like we have seen, it is sp2 hybridized, and therefore nucleophile can approach this carbocation equally from both the sides. Which both sides we are talking about? So we are talking about the side of the leaving group and opposite side of the leaving group. Both are accessible whenever you have flat intermediate. If the intermediate from the chiral alkyl halide survives for a longer time, then there are more chances that you will get a mixture, enantiomeric mixture as a 50-50%, or will say that you will get a racemic mixture will be formed, and at that time product will be optically inactive. But if you do not get 50-50% mixture, There will be always two mirror images, enantiomers, but their percentage may not be 50% or maybe 50%. If it is 50%, we say that it is a racemization is happened, and we'll say that the product is optically inactive. But if you get one form as a 60%, another form as a 40%, then product will be optically active, but you will not get 100% optical activity, because some percentage will be racemization and some percentage will be either with retention or with the inversion. What is retention? Whenever your leaving group and nucleophile come are on the same side, we say it is a retention of configuration. And if it is coming from opposite side, we'll call it as an inversion of configuration. So if I take an example now here, where we have a chiral center over here. What is chiral center? So a carbon is attached to 4 different groups. You can see here it's attached to methyl, ethyl, N-propyl and Cl. Now we know that Cl is a leaving group for us. So obviously this is going to depart. Let's say this is S enantiomer. How do you find out this? So you have to give the priority orders. In this, among this, all these are carbon atoms, but this is Cl. Atomic number of Cl is greater than carbon. So first priority will be given to this, and the last priority will be to the methyl. Second priority will be to this N-propyl, and then third priority will be to this ethyl group. So 1, then you have 2, then this is your 3, 1, 2, 3, going in clockwise manner. But methyl, the last priority group, is beta, therefore it is R goes to S. The first step after departure of leaving group, you get a carbocation which is planar. Here carbon has no positive charge. Now what will happen? The nucleophile, that is I minus, iodide, is going to attack. Now attack can be from left or right, or from the same side of the leaving group or the back side of the leaving group, whatever you get. In the first step, that is step 2, you get these products. Both are nomenclature is same, only their configuration at chiral center is different. It is exactly opposite. One is R, other is S. So if Cl to the same side of the leaving group, the configuration is retained over here, and we say that there is retention of configuration. If your iodide is now coming from opposite side of Cl, you get a product with R configuration, and we will say that this product is with inversion of configuration. So these two are the mirror images of each other. So if I take this particular reaction, what you'll find that locate a carbon where the leaving group is attached. This is my leaving group. So reaction is going to happen over here. After the leaving group departs, I'll get a carbocation at this position, and the methanol will attack here. Methanol has a hydroxyl which is electron rich, and you get product here. Ether will be obtained as a product. Now ether can come from alpha side or it can come from beta side, because we are talking about cyclohexane, and you know in cyclohexane you have two sides. One is alpha, other is beta. Br, since it is at alpha side, then after departure, the carbocation can be attacked by methanol from both sides, that is alpha as well as beta, and you expect these two products in this reaction, which is SN1 mechanism. So now it is just now I told you that nucleophile concentration does not affect SN1 reaction. Why? Because RDS involves only substrate, rate is directly proportional to only concentration of substrate, and therefore concentration of nucleophile does not affect the rate of SN1 reaction, and therefore it is called as a unimolecular. Unimolecular means its rate depends only on one molecule concentration, that is your substrate. Then it is observed that polar protic solvents like water favor this reaction. This is because these solvents are involved in the stabilization of transition state as well as in the stabilization of carbocation. Generally, water is used as a solvent for SN1 reaction, and therefore many times such kind of reactions are also called as solvolysis reaction. If I use methanol as a solvent, that is called methanolysis. Just now we have seen one example in the previous slide where methanol was acting as a nucleophile and also as a solvent. then that reaction is called as methanolysis. And if water is used, we generally call it as a hydrolysis, or any other solvent if used other than, let's say, water or methanol, we can generally call it as solvolysis. So one more, just this is another example where we are shown here methanolysis, or this is hydrolysis, where now water is acting as a nucleophile or solvent is acting as a nucleophile. This is another example. Now see, what are the factors? So we have seen that the structure of substrate matters. The tertiary alkyl halides will react at a faster rate as compared to primary or secondary. Second, we have seen that the solvent effects, polar protic solvent, favor this reaction. Third thing, we have seen that generally concentration of nucleophile does not affect the rate of SN1 reaction. And the last one factor is a leaving group. What kind of leaving group you have? That also affects, because departure of leaving group takes place in rate determining step. In the slow step, therefore good leaving group will always enhance the rate of SN1 reaction. So what you'll find that if the leaving group is it's a good leaving group, then the reaction will be at the faster rate. So generally it is observed that weak bases are good leaving group, and therefore they enhance the rate of reaction as compared to strong bases. So the last factor we are talking about is a leaving group. So if I have, let's say, I have a leaving group halogens, I minus, Br minus, Cl minus, and F minus are my leaving group. If I take alkyl fluoride, alkyl chloride, alkyl bromide, and alkyl iodide, I'll find that alkyl iodides will react at the fastest rate as compared to bromide, chlorides, or fluorides. Why? Because iodide is a very good leaving group. Then you have bromide, then you have chloride, and then you have fluoride. Fluorides are the worst leaving group, and therefore the rate of reaction is very slow with alkyl fluoride as compared to alkyl iodides. So you can see here one example. Again, the leaving group over here NH3 plus, and this is Br. Now if I compare between this, anything which is positively charged will be a better leaving group as compared to neutral. Since there is a neutralization of charge after departure, this reaction will be at a faster rate as compared to the other reaction where bromide becomes a leaving group. So living group, we have seen how it affects. And nucleophile, just now we have discussed that, let's say you have a nucleophile as a water, you have formic acid, then the rate of reaction will not be same, because more polar formic acid, so the reaction with formic acid as well as with water will be faster. So little effect of nucleophile is also observed if you have a solvent as a nucleophile. So recap, if I check this, this is a chiral, optically active, it becomes a chiral, becomes a sp2 hybridized, and you can get the product. But over here, the product is also a chiral because it is formed as a racemic mixture. So this is how we represent reaction. This is one more example. I want you to study this example and understand how you get this product. One is with retention, other is with inversion of configuration. These are the few questions asked based on SN1 mechanism. Kindly try to answer these questions. We have already discussed about this, and it is there in the slides also. So understand and try to write answers for these questions. Thank you. Next time, in the next module, we'll be talking about SN2 type of reaction as well as SNI type of reaction.